Hello, this is Roger Miller. Just final demonstration model, finally everything all put together on this. This is actually I've got two different ideas that I'm working on for propellentless propulsion. This is actually the first idea that the concept kind of hit me in March of 1990. I mentioned that in a couple of different videos before. So just to kind of give an example of, this is based off of Einstein's special relativity equations, specifically the fact that the famous equation that proves that matter can't be cannot be sped up to go the speed of light, because it would take infinite amount of energy in order to do that. That's the the 1 over the square root of 1 minus v squared over c squared. Anyways, the concept here is that the faster an object moves, matter moves, the more force it requires to move it even a little bit faster. So like to go from 0 to 1 mile an hour takes a set amount of energy, but to go from 1,000 to 1,000 to 1, it's only a 1 mile per hour increase, but it's actually going to take a little bit more energy to do that. And really, we don't see that at normal speeds, human speeds. This happens actually as you start approaching relativistic speeds. Start approaching half the speed of light kind of situation. But the equation shows that it is there even at slower speeds. So anyways, the concept here is we've just spin around. We got these weights here, here, here on this first reel, and then on the second one, I've got another one in the back where it's the exact opposite. And there's a little, I should spin this around. There's something to actually cause so that this is the weights here, and then closer than that. So when this one turns, the other one goes in the opposite direction. So I'll show it like this. So we go back to this as we go here. Just see. So we get right there. So anyways, we get it right here. And so again, as this travels all the way around to this point, it's a lot further distance than this weight going from here to here. So I'll just kind of show you real quick here. See how the weight goes this long distance to go all the way around, just a quarter of a turn. So on the other side, it's the exact opposite. So it's actually taking more force as this is spinning to push this down than to pull that up. So because it's going faster. So if you actually got this spinning like this, you could actually get it so that, and here, let's go ahead and get this going here. So see, as this is going around, and you get this faster and faster, the goal is to get this going extremely fast, so a lot bigger engine than this, and actually get this going. And the concept here is that you put this in space, gravity's taking more force to push this side, more force to put that side. For Newton's equation for every action is an equal and opposite reaction. Means that we'd actually be creating a push and actually moving up this direction, because it's taking more effort to push down, equal and opposite reaction. This would actually be pulled up. So that said, just go ahead and turn it off. So that's the concept behind this. Again, the question here is, how big can I build this, and how fast can I get it so that we can actually start seeing some significant speed? So this moving right now, it's just minuscule. If I would be able to get this moving fast enough, it should actually create a upward force. With this one pulling down and this side pulling down, it would actually create an equal push up. And I believe that's actually one of the ideas for future space travel. Well, it's got to be propellentless propulsion, and that's been in the news quite a bit lately. But I think this one's actually based off of Einstein's equations. So the only thing stopping us is our ability to build a device that would take advantage of it. And that's kind of where we're at now. This is a demonstration model. next series or next thing to do is try to see if I can get a huge engine on this, get something a little bit more firm that can handle speeds of maybe 10,000 rotations a second, or 10,000 revolutions a minute, and a second would even be better. But I don't think that's physically possible with materials. But we can figure out something to make this work. That's the idea. Thank you.